Alright guys, in this video we're going to be exploring the concept of a mathematical sequence. And so if you've ever heard or just used this word sequence before in English, I suppose it means that sequence of things are just set of things that are coming in order. And so when we talk about a sequence in math, it's very, very similar, except for we talk about sequences as being an ordered list of numbers. So I can give you an example here in terms of a sequence, so we can write down our very own sequence here. I'm going to say that I'm going to write a finite sequence here, and we'll get into the nitty-gritty of that later. But what if my finite sequence were just this set of numbers right here? Some things that I would maybe want to say about this set of numbers is that there are 5 of these numbers. They're separated by commas, and I can tell which one comes first and which one comes last just because of the order that they're given in. So this would be considered to be a mathematical sequence simply because I have an ordered list of numbers. Now specifically, what is it that makes a sequence a sequence? That's what we're going to really kind of parse out now. So we say, what is a sequence here? We're definitely going to make sure we record that it is an ordered list of numbers. However, what I want you to know is that technically it is a function. Okay, so we're also going to make sure we write this here. A sequence is a function whose domain is the set of counting numbers. And so you're going to see us talk about the counting numbers today. The counting numbers, simply put, are the numbers that you learned when you started to learn to count, and you simply start with 1. So with respect to what we talk about as being a sequence here, let's continue to read. We say that a finite sequence is a function, okay, so it is a function that has a limited number of terms whose domain is the set of 1 through n here. And it says that the values in the range are called the terms of the sequence. So some things here. First one is going to be this. When we talk about what are these numbers that occur in a sequence, we refer to these as being the terms in our sequence here. And so you can see that I have a first term, a second term, a third term, and so on and so forth. This particular sequence only has 5 terms. And so we refer to these as the terms of the sequence. And with respect to this being a function whose domain is the set of counting numbers here, what I'm going to point out is that because these numbers are in a given position here, we're going to interpret our domain as kind of describing the position of each of these terms here. So let's go ahead and illustrate this in a different way. What we're going to do is we're just going to make a table here. And in our table, we're going to put on the left here, we're going to write our term position. And on the right, we're going to write our term value, because I really want you to see this as an input-output relationship here. So when we talk about term position, our domain or input values here, we look at this as being where these terms are located. So my 2 is the first term, and our 4 is the second term, and we have our third term, our fourth term, our fifth term. What are the values of the first through fifth term? Well, the value of the first term is 2, the value of the second term is 4, and we have 6 and 8 and so on and so forth. You can see that this is really just a mapping of input to output, where in a functional sense, we're just kind of saying, look, if you tell me the term's position, I can tell you the term's value. So we're going to refer to these here as our domain values. And again, just want to illustrate or really make this clear. Our domain values represent position, and our range values here are going to represent the term value. So generally speaking, you're going to see us represent some sort of a sequence as something where we have these A's or B's or C's. We say A1 plus A2 plus A3 plus A4, all the way out to maybe the nth term here. But these would be the term values, and these little subscripts indicate their positions within the sequence. So again, a sequence written in roster notation that way can be written more along the lines this way. The position of the term, which is what we're going to use as our n here. And then our a sub n, this is the value of the term in the nth position. Okay, so generally speaking, we're going to see that we have a 1, a 2, a 3, a 4, all the way out to maybe we go to the nth term here. But we get an A1, an A at 2, the value of the third term, the value of the fourth term, the value of the term in the nth position, generally speaking. So when it comes to what is a sequence, generally speaking, is just a function whose domain is the set of counting numbers. Now, let's get beyond this. What are some differences in the sequences we're going to see? You're going to notice that we refer to a finite sequence up here. And when we talk about a finite sequence, we talk about it as having a last term. When we talk about an infinite sequence, you can see that we give an illustration of a finite sequence here. An infinite sequence would be something like this that has this ellipsis right here, which indicates that it never stops going. So what is the difference between a finite and infinite? We'll read the definition here. An infinite sequence is a function that continues without stopping and whose domain is the set of positive integers or counting numbers. So we give these examples down here. Here's the neat thing about sequences. We certainly can write them out this way. They certainly a lot of times do have patterns, but the fact is, guys, they are functions, which means that we can actually come up with a rule that would tell us how to map our inputs to our outputs. So using our function notation here, I want you to see that really what's happening is we're taking the position of something, this n here, and we're plugging it into a rule. And what that rule does is says, here's what you do to your n value to get to the value of the term in the nth position. And so we're going to be using what we call a sequence rule. So for both of these sequences here that you see here, these 2, 4, 6, 8, maybe it ends and maybe it doesn't end, we say that a sequence can be specified by an equation or rule. For example, both sequences above can be described by the rule a sub n equals 2n or f of n equals 2n. So you can see that in the rule above here, we can see that f of n, our rule, was double the input value or double the position, and what you get is the output value here. And you can see that rule works. Another way to write this rule is with this little subscript here, a sub n equals 2n, and I want you to know that this notation here is the same no matter if we use function notation or if we use sequence rule notation. So we're going to make sure that we take a moment here and write down the definition for a sequence rule. And we're going to say a sequence rule, a rule that states what, states algebraically what to do to the term position input in order to find the term value, which is our output or range value here. So what I've got here is just a couple of term rules, and it asks us to write out the first 6 terms of the sequence. And so neat thing here is that on letter A, we already have the rule. And so what I'd like to have us do is just go ahead and make a table here. Because this is a function, we can go ahead and just write this in a tabular format. And we're going to write on the left here n, which represents the term position. And then we're going to write on the right here a sub n, which I'm going to write the rule for here, 2n plus 5. So what this basically states is if you want to find the value of the first through the 6 terms here, we just need to plug it into our rule. And so you can see that this behaves a lot like functions. As a matter of fact, it simply is a function. The only thing that's different between this rule and say any other function is just that what are you allowed to plug in for your inputs here. When it comes to a function, you're kind of allowed to plug in any x value that you want to, but when it comes to a sequence, we can only plug in n values that are counting numbers because those represent the position that the term is in. So looking at these values here, it looks like we get a pretty describable pattern. We see 2 times 1 plus 5 is 7, 2 times 2 plus 5 is 9, 2 times 3 plus 5 is 11. We can see that this really has a well-behaved pattern here that it's going up by 2's every time. So you can see that the first 6 terms of our sequence are 7, 9, 11, 13, 15, and 17. We've written this in a tabular fashion. I would say that it's very also common to write out the first 6 terms as just 7, 9, 11, 13, 15, and 17. This would be the first 6 terms. So which one's more appropriate? I'm going to tell you that you're going to see it written in this roster notation a lot of the time, but what I'd like to see is a table because you're really recognizing that this is a function. So let's take a look at one more here. I want to take a look at this one just because it's a really good example of an exponential type of function, and in this case we're still going to make a table and write out our values of our first 6 terms here. And you'll notice that this time we're not having a sub n, we have f of n as our rule. So f of n equals -3 is our base to the n minus 1 power. So what this means is if you want to find the values of your first 6 terms, we have to go plug these in for n, which in this first case gives us a -3 to the 1 minus 1, which is really -3 to the 0, which is 1. I'm going to box that here. Look what happens as we start to raise our power of n here. So -3 to the 2 minus 1 is -3 to the 1, which is -3. As far as we're concerned, we keep going here, we get -3 to the 3 minus 1, which is really -3 to the 2, so we get a +9, and we'll see if we can start to pick up on our pattern here. -3 to the 4 minus 1, which is -3 to the 3rd. This time we get 3 cubed, which is 27, but it's negative. So you can see that we're getting powers of 3 here, and it's alternating signs. So positive 1, negative 3, positive 9, negative 27. If you take that times 3, you're going to get a positive 81, and if you take that times 3, you get a negative 243. So you can see that not all of our sequences behave the same way. We tend to get sequences that behave differently depending upon what their rule is. So 1, negative 3, positive 9, negative 27, positive 81, negative 243 were the first 6 terms of the sequence here. So what I'd like to challenge you to do for the next time I see is this. If I gave you these 3 rules right here, b of n or b sub n, f of n, and a sub n, could you write out the first 6 terms of the sequences just to make sure that if you know how this rule works, if you know the term position, we can find the term values. Cheers.